So hi everyone. So now we will see geometry of SVD, okay, which means how SVD is working geometrically, right? So you might remember SVD, right? So what is the SVD? SVD is singular value decomposition, okay? So let's suppose that you have a matrix A, and then in this matrix you want to apply SVD, right? So suppose you want to apply SVD, then what will happen? You will say that A can be decomposed into U sigma and V transpose. So let's suppose A is M cross N matrix, then U will be some dimension, sigma will be of some dimension, and V transpose will be of some dimension. Can you tell me what is the dimension of U? It will be M cross M. This is M cross N, and then this is N cross N, right? This is N cross N. That is how it is working, right? Okay. So now let's suppose given this SVD, we want to analyze this geometrically. Okay. So that is the aim or that is the goal of this particular video. Okay, real. Okay, so let's just continue. So basically, we want to do SVD on this, right? Now, we know one thing. Suppose that we have a vector, which is let's suppose x. And now, if we multiply this vector by some matrix, let's suppose A, then what will happen? Do you remember what will this matrix do to this x if we multiply a matrix x to this vector to matrix A to this vector x? Then what will this matrix do? So basically, this matrix might rotate and might stretch this x. So which means now your ax will be looking like this, okay, or might be looking like this. So basically, this matrix will just rotate it, and also it might shrink or stretch this vector, right? So this is what matrix does for a vector. Now what we will be doing, we will be just breaking, okay, so I can write it. We will break this phenomena, whatever is happening here, okay, into three parts. We will break this scenario, this into three parts, which means instead of looking that what is this A doing, instead of looking like this, what we will be doing, we will be looking like this. We will be seeing that what is this U is doing, what is this sigma is doing, what is this V transpose is doing. So first part, second part, and third part. So we will be just breaking this whole phenomena into three parts. Is this clear to everyone that what we are trying to do? So we are trying to understand that what are the matrix does on a vector, right? That's what we are trying to understand. Okay, so this is the goal, but we want to understand this geometrically. Okay, so I hope the goal is clear to everyone. Now, as I said, like we will be just breaking this into three parts, right? Now, U and V are the orthogonal matrices, as you might know. Okay, as you might remember that U and V are the orthogonal matrices. So let me first tell about the properties of the orthogonal matrices. So there are two properties which are, to be honest, not very important. Okay, but just for the sake of information, we are seeing this. Okay, so these are the two properties that we have. Now these two properties might not be much important, but still we want to have a look on this. So one property is saying length preserving. So which means orthogonal matrices are length preserving. Do you know what is the length of vector? Do you remember? So length of vector is basically, if let's suppose this is in R2, okay, which means the length of the vector will be square root of x1 square plus x2 square. You might remember this, right? Second property is angle preserving. So let me first tell you that what does this length preserving and angle preserving properties mean. Okay, so let's just first talk about the first property, which is length preserving. It says that whatever length x has, okay, suppose x is some vector and whatever length x has, the same length will be given by u x. U here is orthogonal matrix. Okay, so what is orthogonal matrix? So u is orthogonal matrix, which means u into u transpose is identity. Okay, so this is identity matrix. So that is what, suppose u is like this. Now we want to prove that if you multiply this x by u, then the length of the x doesn't change. This is the simple proof that we want to have. So, any idea how we can prove it? So that's very simple. What you can do, you can just talk about x square. So instead of proving like this, you can talk about x square. Okay. Can I prove like this? X square is same as ux square. Okay. Can I prove like this? So basically, I will be going in this proof that, okay, the length of the vector, which is like either I prove a square root of x1 square plus x2 square, or I'm just proving that x1 square, this is x1 square plus x2 square. And I want to also prove that this is also x1 square plus x2 square. Okay. This is my proof that I want to do. So let's just see that how we can do it, right? So do you remember that how to write this x square, this particular length in the vector dot product form? You might remember little bit. So how to write it? Basically, basically you will say that we can do one thing. We can just, write this x square as, you can write this x square as x transpose x, right? And how you can write ux square? You can also write it as ux transpose ux. I hope that is fine to everyone. So x square means x1 square plus x2 square. Okay. And here also it means x1 square plus x2 square. So both of the meanings are same, right? So here also it is x1 square plus x2 square. Basically, you can write it like this. Okay. So, oh, so basically, I want to prove, okay, the proof that I want to do is basically that if you multiply even with u, then the length doesn't change, which means these two are same. This is to be proved. Okay. So I can say this is to be proved. So I hope that is fine. That what we want to prove, right? So this is what we want to prove. So basically, we started with this that x square can be written like this and square can also be written like this. Now we want to prove that both are actually same. So this is a simple proof. So just give it a try and see if you can prove this. How to prove it? See this. This ux transpose will be nothing but x transpose u transpose, isn't it? And then into ux, right? So this is u transpose u, which since this is orthogonal matrix, that is why this is x transpose x, which means this is same as x transpose x. Very easy to prove, isn't it? So you can say this particular thing is actually same as x transpose x. So which means this is nothing but since this is just x square, right? This is nothing but x square. So hence we have proved that if you multiply a vector x with let's suppose some matrix u which is orthogonal. Okay. So u is orthogonal matrix. Then it may rotate. Okay. It may rotate this x. Probably the x or sorry ux will look like this, but the length won't change. Okay. So it may rotate, but the length won't change. So you can say length won't change here. Okay. That is what length preserving means. And we have just proved it because this is very simple proof. So this is very simple to prove that u where u is a orthogonal matrix, u is length preserving, right? U is length preserving. Now let's just prove that this is also angle preserving. Okay, not just length preserving, also angle preserving. So I told you these are the two properties. What are the two properties? One is length preserving, another one is angle preserving, right? So let me write it. Okay, these are the two properties. right? Now we have talked about the length preservation, which means if you multiply a vector x with u, then length of the x and length of the ux are actually same. Okay. The second property is angle preserving, which means it says that if you have two vectors x and y, and whatever is the angle between x and y, okay, whatever is the angle between x and y, if you multiply u, one thing we know, what will happen to x? It can be rotated only. It cannot be stretched. It cannot be synced, which means that length won't change. So it can be rotated. That I completely agree. Okay. And y will also be rotated, but they are saying the angle will also be not changed. So which means, which means that if you have this as x and y, and then if you multiply by the u, then they may be rotated, but the angle, if this angle is theta, then after multiplication, whatever you are getting, you will getting ux and uy, right? Then this angle is also theta. That's called angle preserving. Okay, understood. So now let's just prove that how to, how to visualize or how to basically mathematically prove that this is also angle preserving. Understood. So we want to prove the angle preserving also. So let me go to the next page, which is angle preserving. Okay. So what I can do, I can just copy this diagram on the next page also. So how to prove this? How to prove this? It is also easy to prove. Do you remember what is the dot product between two vectors x dot y? You might remember this, right? This is, one way to write like this, which I completely agree. Other way to write like this. Okay. Other way to write like x dot y is like this: length of x into length of y into the angle between them, right? Cos theta. You might remember this. Okay. So, so one thing is for sure that x dot y and see the dot product actually doesn't change, then the angle will also not change. So basically, one thing is for sure that if you have, x dot y, and then if you have ux dot uy, okay, and then you have ux dot uy, the angle, the dot product between these two, it will be basically ux transpose into uy, which is same as x transpose u transpose uy, which is same as x transpose y. So basically what I'm saying that this particular quantity, if you do the dot product between ux and uy, it is same as the dot product between x and y. So basically these two dot products are same. I mean, these two quantities are same. So these two dot products are same. So hence what we can say from here, hence dot products are same. Okay, ux dot uy. Now let's just apply the second definition of the dot product using the angle. Okay, so since the dot product are same, now I want to prove. Okay, the proof has two parts. One is to prove that dot products are same, which we have just proved. Now we are in the second part of the proof, where I want to show that the angles are also same, which is also easy to prove. See here, x. I'm applying the another definition. Let's suppose here the angle is maybe alpha. Okay, let me change the color of the pen, and let's suppose here the angle is beta. Okay, so this, this is the length. It is also the same as, see, the length doesn't change, right? So length of x and length of ux is same. Basically this is same as length of x, this is same as length of y. Okay, and then cos beta, and here you have x, I mean as it is, here you have as it is, right? So from here can you say that cos alpha is equal to cos beta, which means alpha equal to beta, right? Is this fine to everyone? I mean, I'm just doing one-to-one comparison, so that's fine, right? Okay. So basically, what is happening here? Here, I just proved that the angle is also same. Alpha was the angle earlier, okay, between x and y. Alpha is the angle between x and y. Beta is the angle between ux and uy. And we have just proved that angle is also same. which means in conclusion, if I just conclude, length preserving and angle preserving, okay, length plus angle preservation means, it means what? That if you have, let's suppose, two unit length vectors here, okay, I mean it could be any length, I'm just saying it is unit length. If you have two unit length vectors here, here also, or whatever length here it is, okay, here also you will be getting same length, it will just be rotated. So basically it, see, the x cannot be stretched or x cannot be shrinked, right? Similarly for y, so basically x can be rotated only, y can be rotated only, it cannot be shrink or stretched. And another interesting fact is that both will be rotated at the same angle, because the angle has to be maintained. So basically if you have to rotate, so the ultimately what u is doing to any set of vectors, you can take any set of vectors, I'm currently taking two. So what u is doing, u is basically saying that I will just rotate the whole phenomena. Okay, so this is what u is doing. Okay, it is just saying that I will just rotate everything, I will not change the angle, I will not change the length, so I will just rotate the whole frame, that's all. Okay, so you just rotate whole frame without changing anything else, right? So that's what angle and length preservation mean. Okay, so let me quickly go through this proof. What is the angle preservation? It means that whatever is the angle between x and y, it should be same. Okay, so we have used two different definition of the dot product. One definition is this, second definition is this. Now, using the first definition, we have proved that okay, dot products are same. Okay, so part one, prove that prove that dot products are same, which is, that is that is x dot y is equal to same as ux dot uy, right? So this is the part one. What is the part two? Part two is to prove that actually the angles are same. Okay, so using this definition of the dot product, we have proved, okay, the angles are same. So what is the part two? Using, let me change the color. Using the previous result, prove that, okay. So anyway, ultimately this is the conclusion, that this is important conclusion, that if you are having orthogonal matrix, okay, then it is just going to rotate the frame, that's all, it will not do anything else, it will just rotate the frame. Okay, anyway, as I told you, it is not too important, but it is okay to keep this thing in the mind. Okay, so basically it is length preserving and angle preserving, right? If it is orthogonal matrix, what is the orthogonal matrix? It means u transpose u is identity. Okay, and if I want to find out the determinant of the orthogonal matrix, then you will say determinant will be either plus 1 or minus 1. Why? Because here this is same as determinant of u whole square, because determinant of u transpose and determinant of u are same, right? So that is why determinant of u whole square equal to 1. So from here you can find out the determinant of u. It is going to be either plus 1 or minus 1. Okay, so determinant is either plus 1 or minus 1 for the orthogonal matrices. Okay, so coming back to the topic, which is that geometry of SVD, right? I mean, how this SVD is behaving. So as we told that we will just break this into three parts, right? U, sigma, and V transpose. So let's just do it, right? Okay. So now Now, you might little bit remember that we have already talked about this, that these are the bases, right? These are the bases. Okay. So, before I jump into the SVD geometry, let me little bit tell you about the eigenvalue decomposition. Okay. So suppose that there is a vector x, okay, and there is a matrix A. Suppose A into X. Suppose that A has, okay, assume A has, let's suppose this is 3 cross 3, okay, or 2 cross 2, whatever. So suppose this is 3 cross 3. So A has 3 linearly independent eigenvectors. Okay. Suppose A has 3 linearly independent eigenvectors, which means since it is 3 cross 3 and 3 linearly independent eigenvectors, now you tell me, can I write this X? Suppose these eigenvectors are uh, E1, E2, E3, or what? Okay, E1, E2, E3. Okay, E1, E2, E3. These are not standard basis vectors. These are the eigenvectors. Suppose A has some eigenvectors, right? Something like this. Can I write this X? Okay, since these are 3 cross 3, X is A is 3 cross 3 matrix. So can I write this X as a linear combination of these three vectors? Because since you have three vectors and these are in R3, so you are filling the space, right? Right? You're filling the space. So it means what? It means that X can be written as a linear combination of these three vectors, maybe alpha 1, alpha 2. Is this fine to everyone? X can be written as linear combination of these three vectors. Okay. So now given that X can, because see, I'm assuming that A has three linearly independent eigenvectors, right? Now, which means what? It means that you have three vectors in R3 which are linearly dependent. It means that you can fill the space, right? So basically, this is also called as eigenspace. Okay. This is also called as eigenspace. Here, eigenspace is actually R3 itself. Okay. I mean, eigenspace is basically the space or the vector space given by the eigenvectors. Since they can fill the whole space, so that is why it is R3 itself. Okay. So all of you agree on this point that X can be written as a linear combination of these three vectors because these three vectors can fill the space. Now you multiply by A. Okay. What will happen? This will be A alpha 1. So I'm writing the alpha 1. Since alpha 1 is the scalar, you can write it anywhere, doesn't matter. Right? Okay. So what is this? A into even. See, if it is eigenvector, then this is lambda 1 even. Or if we are, little bit confused about even, then let me write V1, V2. Okay. So I can use the another term like V1, V2, V3, which is fine. If because even E2, E3 are generally used for the standard basis, right? For the standard basis. So I can quickly write it V1, V2, V3. Okay. Suppose this is V1, this is V2, this is V3, right? So it is basically V1, this is V2, this is V3, this is V1, this is V2, this is V3, right? So if V1 is the eigenvector, can I write lambda 1 V1? Now AV1 is lambda 1 V1. AV2 is lambda 2 V2. AV3 is lambda 3 V3. Right? So what is happening here? That AX is coming out to be some linear combination of V1, V2, V3 again. Some linear combination of V1, V2, V3 again. But now the coefficients are not as same as X. X had the coefficient alpha 1, alpha 2, alpha 3. But what are the coefficients here? Lambda 1, alpha 1, lambda 2, alpha 2, and lambda 3, alpha 3. So basically, what I'm saying here is that Suppose b1, b2, b3 are the eigenvectors, then they can fill the space, right? So I'm using this b1, b2, b3 to fill the space. Okay, and then x can be represented like this. Then ax will be like this. Okay, ax will be like this. Now suppose uh, if I multiply a again, if I multiply a again, then what will happen? It will be a square x. If I multiply a again, it will be a b1, which means lambda 1 b1 again, right? So you can just check it. Alpha 1 will be as it is. It will be lambda 1 square b1, okay, plus lambda 2 square b2, alpha 2 lambda 2 square b2, plus alpha 3 lambda 3 square b3. Similarly, you can keep on doing it. If I let's suppose do a power 10x, then it will be alpha 1 lambda 1 power 10 x v1, okay, plus alpha 2 lambda 2 power 10 v2, plus alpha 3 lambda 3 power 10 v3, right? So basically, if you have this x and if you keep on multiplying by a, then you will be keep on getting something like this. Okay, you will be keep on getting something like this. So this is just for the, I mean, practice. So I will come to that, but for now we can just remove this part, right? So I will come to this multiplication part in a while. Okay, in a while. Okay, now let's just talk about this. So suppose you have this. Okay, so you multiply by the a, you are getting this. Can you tell me geometrically, or at least can you tell me with the, with the angle of different bases, that what is happening here? See, if you represent this x, if you represent this x in the basis of b1, b2, b3, what are the coordinates? Alpha 1, alpha 2, alpha 3, isn't it? If you represent this x in the basis of, v, where v is v1, v2, v3, what are the coordinates? It is alpha 1, alpha 2, alpha 3. I hope that is fine to everyone, right? Alpha 1, alpha 2, alpha 3 are the coordinates of x. Now, if you represent ax, in the same basis, okay, which is the eigenbasis, which is v, then what are the coordinates? The coordinates are alpha 1 lambda 1, alpha 2 lambda 2, alpha 3 lambda 3. So which means the coordinates are almost same. It is just that lambda 1, lambda 2, lambda 3 are getting multiplied by these three dimensions. So what a matrix is doing to any vector? So this matrix were a square matrix or having the three linearly independent eigenvectors, which is fine. But in like I can say like these kind of matrices, what these kind of matrices are doing to a vector, they are saying that if you look at the vector with respect to a different angle, with respect to the basis of eigenbasis, you can say, or with respect to the basis of eigenvectors, then the coordinates, whatever the earlier coordinates you had, right? These coordinates are getting multiplied with the eigenvalues, which means what a matrix is doing to a vector is nothing but these coordinates, they are basically changing the coordinates, and these coordinates are getting multiplied by the eigenvalues, right? But obviously, these are not the standard coordinates. The standard coordinates are this. I mean, ultimately, whatever you are getting are the standard coordinates or standard basis coordinate. But yeah, if you look at this x and ax with respect to the eigenbasis, then this is the coordinate with respect to eigenbasis, and these are the coordinates with respect to eigenbasis. So now you see the similarity. Okay. So if you just change the basis, if you look at ax or and x in the like, if you look at the way that what a matrix is doing in the eigenbasis, then you will be easily able to look at the results. So what matrix is doing? So you can say, see, that's very important observation. Now you can say what matrix is doing to any vector. So you can say that A is uh, multiplying the coordinates with the eigenvalues, right? So basically, A is multiplying coordinates of x with corresponding eigenvalues. Is this statement 100% true? Is this statement 100% true, or should I write something? Should I write something? So this happens in which basis? In eigenvector basis, right? Eigenvector basis. This is happening in eigenvector basis. So if you look with respect to the eigenvector basis that what is happening, then you will get to know that okay, this is happening. Now, if you keep on multiplying the a, right? If you keep on multiplying the a, so now what are the coordinates? What are the coordinates of a power 10? These are the coordinates, right? You will say it is alpha 1, lambda 1 power 10, alpha 2, lambda 2 power 10, like this, right? Alpha 3, lambda, sorry, alpha 10, lambda, or maybe if these are the three coordinates, yes, then alpha 3, lambda 3 power 10, right? So, so these are the coordinates of a power 10 x, but not the standard coordinates, obviously. These are the coordinates with respect to v1, v2, v3. Okay. So I hope that is all of you should agree on this. So this is what a matrix is doing to a vector. Now suppose this one of the lambda, okay, let's suppose lambda 2, lambda 3, these lambdas. Suppose these lambdas are less than 1, then what will happen to coordinates of this a power 10x? So suppose some of these lambdas, right? So suppose lambda 1 is okay, let's suppose lambda 2 is less than 1, lambda 3 is less than 1. So these, the moment you took more and more power, right? So more and more power will degrade the value, right? Keep on reducing or degenerating, I can say. Right. So basically this is happening. I mean, you can say that okay, what is happening when you are multiplying a matrix with a vector, then you can say it is easy to talk in terms of the different bases. Sometimes it is easy to talk in terms of the different bases. If you want to talk in terms of the eigen basis, then you can quickly tell. Okay, what you will be telling in terms of the eigen basis. Can you tell me immediately that what a matrix is doing to a vector? You can tell me that okay, a matrix is doing nothing but multiplying by the eigenvalues to the corresponding coordinates. That's all, right? Multiplying the eigenvalues to the corresponding coordinates in terms of the eigenbasis, right? In a standard basis, yes, you can, I mean, you cannot directly visualize in terms of the standard basis, but yeah, in the eigenbasis, at least you are doing so, right? And the more you keep on doing the power, then the more like you will say that one of these coordinates will keep on reducing, and one of the coordinates will keep on increasing. Okay, if it is, let's suppose, greater than 1, okay, then few of the coordinates will be keep on increasing, few of the coordinates will be keep on reducing, right? So that is what happening if you multiply a matrix with a vector. But now let's suppose a matrix is not exactly the square matrix, so you don't have eigenvalues and eigenvectors, but yeah, you have singular values. Okay, so now suppose a is not a square matrix. Okay, so here instead of ax equal to lambda x, okay, a is not a square matrix. And what do you have here? So instead of ax equal to lambda x, what do you have? Av equal to av1 equal to sigma 1 u1, something like this, right? You might remember. So if a is not a square matrix, then you will be having something like this. Okay. Now let's just see that how to analyze these things. Okay, if a is not a square matrix, in that case you can say then we do not have eigenvectors and all, right? We do not have. Now as we know that a is, suppose if it is not a square matrix, then this is m cross n matrix, then it will be u sigma v transpose, and then in this case it will be m cross n, and then this will be n cross n, this is m cross n, right? Okay, so you have n cross n matrix here, which is orthogonal matrix, right? Suppose you have X. What is the dimension of X? X will be n cross 1, which means it is in Rn, right? It will be in Rn. And we already have the complete basis for the Rn, which is V, right? We already have the complete basis for the Rn because we have all these vectors are orthogonal to each other, right? So these vectors are linearly independent and in fact orthonormal. Okay. These vectors are basically orthonormal. So which means you already have the basis for Rn. It means if you have Ax, okay, X is in Rn. So can you represent this X as a linear combination of B1, B2, B3, B4 till n? Suppose these are only three. Is this fine to everyone? Because B1, B2, B3 are basis for R3, right? Because dimension of B is 3 cross 3 and these are the basis for R3. I mean, because linearly independent, orthogonal, everything is there, right? So suppose again, these coordinates could be anything. Okay. So maybe I can make it alpha 1, alpha 2, alpha 3. I mean, basically, these are the coordinates of X, right? With respect to V1, V2, V3. Or in other words, you can represent this X as a linear combination of V1, V2, V3 because V1, V2, V3 fills the space. Okay. Because V is basically 3 cross 3 and B1, V2, V3, these are linearly independent, hence fills R3, right? So basically, given any vector X, you can represent like this. That's my point. Okay. Now let's just see what's going to happen if you multiply by the A. Here, alpha 1 I'm writing like this, and then there's AB1 plus alpha 2 I'm writing like this, and then this is AB2 plus alpha 3 I'm writing like this, and then this is AB3. Basically, alpha 1, alpha 2 are the alpha 3 are the scalars. So I can write it here or here, doesn't matter, right? Okay. Now what is this AB1? You might remember AB1 is, what is AB1? It is sigma 1 U1. What is AB2? Sigma 2 U2. What is this AB3? Sigma 3 U3. Isn't it? So basically, if I just keep this alpha 1 as it is, then this is sigma 1 U1 plus sigma 2 U2 plus sigma 3 U3. So basically, I'm just telling you that what's going to happen if you multiply this X by A. Okay. Just seeing the things but with a different angle. That's all. Okay. So I'm representing X as a linear combination of V1, V2, V3 because we can do it. And then we know that, okay, AX will be like this, right? Okay. So if you multiply with A, it will be sigma 1 U1 like this, right? Okay. Now, let me do one thing. Let me just put two things side by side. Okay. See, this is the SVD thing, right? This is the SVD thing. And also, let me put what happened when we had the square matrix, eigenvectors, linearly independent, and all. Okay. So basically, this is one side of the story. And suppose we have like this, then this is basically another side of the story. I mean, if this is a square matrix and linearly independent eigenvectors like this, right? Okay. See, the only difference you might be able to notice is that you have here, uh, I mean, we started in the same way, right? We started in the same way. Okay. But the moment you multiply, this AB1 is not alpha 1 V1, oh, sorry, lambda 1 V1. It is just sigma 1 U1, right? That's the only difference. I told you that the coordinates of x with respect to v1, v2, v3 are alpha 1, alpha 2, alpha 3 here. And with respect to v1, v2, v3 after multiplying, okay, it is alpha 1, lambda 1, alpha 2, lambda 2, alpha 3, lambda 3, right? So here what we can say, the coordinates of x initially with respect to b1, b2, b3 are alpha 1, alpha 2, alpha 3. But with respect to u1, u2, u3 after multiplication, you get the coordinates with respect to u1, u2, u3. I mean, now you don't have the coordinates with respect to v1, v2, v3. The reason is very simple, because dimension itself might not match, right? I mean, here the v1 could be 3 cross 3 or something like this. Let's suppose this is, 2 cross 3 matrix. Okay. Then u will be basically, this is 3 cross 1. Okay, the ultimately you will be getting in 2 cross 1, and you will be getting in R2 basically. Ultimately you will be getting in R2. So AX is in R2. Can you have AX, okay, which is in R2? Can you have AX coordinates with respect to B1, B2, B3? No, because B1, B2, B3 are in R3. Okay, because the matrix is rectangular matrix, not the square matrix anymore. So basically what I'm trying to say, that if you have, okay, AX, then you are having the coordinates with respect to u1, u2, u3. You don't have the coordinates with respect to v1, v2, v3, and which is okay, because the dimension might also not match. So what you can conclude from here, okay, what you can conclude, you can say that if you want to look at this AX, okay, with some different angle, so what you will conclude, you will say that what this A is doing to this X, we started with coordinates alpha 1, alpha 2, alpha 3. Okay. We started with these coordinates. Do you all agree with me? Right? We started with these coordinates alpha 1, alpha 2, alpha 3. Now you can also write, okay, just for the sake of completion, with respect to V. Okay. We started with these coordinates, and after multiplication, we got coordinates. And what are those coordinates? Those coordinates are sigma 1, alpha 1, sigma 1, alpha 1, sigma 2, alpha 2, sigma 3, alpha 3. Okay. And these coordinates are with respect to u, because we cannot have v and v here, because the dimension itself might not match, right? Okay. So I hope little bit this is fine to everyone, right? So it might so happen that one of this alpha 3 0, right? It might so happen that one of this alpha 3 0, which is fine. So basically we started with alpha 1, alpha 2, alpha 3. These are the coordinates with respect to v1, v, and now we got the coordinates alpha 1, sigma 1, alpha 1, sigma 2, alpha 2, sigma 3, alpha 3. Okay. Now with respect to u, that's the only change. So basically earlier also the same thing. Okay, we started with the coordinates alpha 1, alpha 2, alpha 3. We got alpha 1, lambda 1, alpha 2, lambda 2, alpha 3, lambda 3. With respect to v, we started. With respect to v, we ended up. Here the output basis is basically different, right? So basically what I'm trying to say here is that this is A is u sigma and v transpose, right? So if you multiply A with x, you will be getting something like this. Right? So basically, I want to tell you that what this B transpose is doing, what this sigma is doing, what this U is doing. Okay. I want to tell you each of this role individually. So basically, this is, let's suppose, V transpose. Okay. So let's just see what this each of this is doing. This is sigma, and then this is U. Okay. So You might remember, by the way, B transpose and V inverse are same in this case, okay? Because this is orthogonal matrix. You might remember that what does this B inverse does? If X is in the standard basis, if X is a matrix, oh sorry, if X is a vector which is in the standard basis, what will this V inverse X will do? Okay, or V transpose X. What is this? If you multiply X with V transpose or V inverse, in this case, you can have anything because both are same. Then you will get an X only, but in the in basis of V. Do you remember this? So this X, these are the coordinates in basis of V, right? I mean, if you multiply with the B inverse. Okay. So how does this work? See, X in the standard basis is equal to X is in this V basis multiplied with the V. So if you multiply V inverse here, you will be getting V inverse into X standard, you will be getting X in the basis of B. You might remember this thing, right? Okay. Now this matrix is diagonal matrix. Okay. This matrix is diagonal matrix. Suppose sigma 1, sigma 2. So let me first tell you quickly. Okay, we have already discussed this, but quickly let me tell you. Suppose you have some diagonal matrix, you have some C1, C2. If you multiply by some diagonal matrix, then what does happen? Then the resultant vector will be sigma 1 C1, sigma 2 C2. Okay. So which means you're taking X in the basis of V. I mean the coordinates in the basis of B. Basically, you have in the standard basis, but yes, this V transpose will convert in the basis of V. Okay. Now first you change in the basis of V, then you multiply by the sigma. What the sigma is doing? Sigma is saying that I will be just multiplying each of the coordinates with sigma 1 and sigma 2 respectively. I mean, if you multiply anything with the sigma, it does this, right? It does this. Okay. So this sigma is saying that I will be just multiplying. Let me just go to the next page and let me just try to break it down. Okay. So that you can understand it better. So you started with this X, which is a standard basis. You will first multiply V transpose. Okay. I mean, first you don't multiply with U. Okay. First you will be multiplying with a V transpose and then with sigma and then with U, right? That's how it works. So now let me first multiply with the V transpose. So if you multiply with the V transpose, you will get a X in the basis of V. Then you multiply with the sigma. Then it will be basically, let's suppose these coordinates, okay, are alpha 1, alpha 2. Okay. Then this will be what? I mean, to start with, it could be anything. Okay. It could be x1, x2. Now this will be what? This thing that you will be getting here will be what? This will be sigma 1, alpha 1, sigma 2, alpha 2, right? If you multiply this, you will be getting like this, right? Okay. Now tell me what does happen if you multiply something with, let's suppose you see, if you multiply something with let's suppose V inverse, as I told you V inverse, then it will be in the standard. I mean, from the standard basis, you can convert to the basis of V, right? But suppose if I write like this, okay. So basically here it will be, this particular thing will be this, whatever you multiply, it will be sigma 1, alpha 1, this vector u1 plus sigma 2, alpha 2, this vector u2, right? That's how you will be doing it. Is this fine to everyone? Okay. So now we need to check what are these, like I mean, what are this final thing is there, right? So basically if you notice this is nothing but the coordinates of the vector with respect to u1, u2, isn't it? And if you multiply the u itself, now this final in the standard basis. I mean, finally this is the standard basis. But if you look at this only, this is the basis of u, right? So basically, what is happening to your vector x? It is first getting converted to the basis of v, where you are actually performing the operation, which is basically multiplying with the sigma 1, sigma 2. And then finally, whatever you are getting, right? Whatever you are getting the basis of u. Yes, ultimately we are getting the standard basis. But if you look at this, just for the visualization purpose, or just with respect to basis of u, then you are getting this, right? Ultimately, it is getting converted to the standard basis. We started with the standard basis; it is getting converted to the standard basis, right? So basically, you can say this is standard basis. This is v basis. This is basically like this. See, from x, if you multiply with a v transpose, you are getting in this. And this is the real thing is this. Okay, this is the real thing. I mean, if you just ignore the basis in which we are talking, this is the actual linear transformation. Okay, you can say this is the actual linear transformation. And what is that? This is sigma. Sigma is the real um shark in the in the house, or I mean, or you can say sigma is a real bull. Okay, it is the main thing which is performing the job. It is saying that, okay, I'm going to multiply by the sigma 1, sigma 2, sigma 3, like this. Okay, it is, these are just change of basis and all, right? And ultimately, once you get in using the sigma, whatever you get using u, what you are getting, ultimately you are getting in the standard basis. Ultimately we get in the standard basis only. Okay, I mean, if you look at this is in the basis of u, but if you multiply with a u, right, then this is in the standard basis, ultimately in the standard. And that is what u is doing. Okay, but for now you just ignore this u and v. Okay, I mean, I will just suggest you, just a second. So I will just suggest you, just for a moment, if you just ignore this, what this u is doing and v is doing. Okay, so just ignore this u and v, right? A real bull is this sigma. Okay, so what the sigma is doing? Sigma is saying that i'm I'm basically multiplying your vector. Yes, it was in the basis of v, but that's fine. Okay, I'm just ignoring the basis. So sigma is saying I'm multiplying your vector with the sigma 1, sigma 2, sigma 3, like this. That's what any matrix is doing. Yes, we can talk about the basis, that in which basis is it doing, and all. Like, I mean, it is doing in the, it is first basically converting into, I mean, you are having a vector, you just see this vector with respect to the basis b. Okay, you just see, okay, whatever vector you have, you just see this vector with respect to the basis b, and then you will get to know that, okay, this vector is actually getting multiplied with the sigma 1, sigma 2, sigma 3, and whatever you are getting is in the basis u. But yes, again, you can convert, definitely you can convert in the standard basis. So basically, this is the whole story of any matrix that is basically doing to the to the any vector. Okay. So let me know if that is understood. So now someone asks you that what a matrix is doing. Any matrix, what this matrix is doing to the vector, then what will you say? You will say it is just multiplying sigma 1, sigma 2, sigma 3. Okay, to the corresponding coordinates. Then if someone asks that, oh, can you tell me in which basis, or can you tell me more, then you can say that, see, you take the vector in the basis of v, multiply sigma 1, sigma 2, sigma 3, and ultimately you will be getting in the basis of u. Yes, you can definitely convert that to a standard basis by the by multiplying the u again, but that's fine. I mean, that's your choice. Okay, so basically what does a do to x? This is the question that you want to answer today geometrically. Now, what it is doing, you can say effectively it is multiplying by sigma 1, sigma 2, sigma 3. But, okay, so in more detail, show in short answer, effectively It is multiplying corresponding coordinates to sigma 1, sigma 2, and sigma 3. Right? This is a short answer. What is the long answer? Okay. The long answer is that if you look at the vector x in basis of b, then a does multiply with just a second. Yeah, with sigma 1, sigma 2, sigma 3, and the coordinates are in basis of u. Are in basis of u. But we further multiply u to convert in the standard basis. V or the matrix A, right? Further multiply with u to convert in standard basis. Okay. So is this idea clear to everyone? Because this is very important. And let me tell you one thing. You may be taking it, very granted that okay, this is a usual thing, but it is really very hard. If you look at any other resource, it will be really very hard to understand it by yourself. Okay, I have done enough analysis. I break it down in the very simple language. So actually, let me tell you one thing. See, this particular, yeah, this particular equations, or this particular, I can say, diagram or whatever. It was actually when I was studying at ISC. Then I used to have one whiteboard in my room, in my hostel room. I used to have one whiteboard. So these equations, I think for 3 4 months, these equations were written on that board. So one day I was solving something and I got to know. I mean, I got to analysis this. I wrote it on the board because I found it very nice. Okay, just for the analysis purpose. Sorry, not this. This one. Yeah, this one. So these three equations. So just for the analysis purpose, I wrote these on the board, and then 3 4 months I didn't scrub it. So yeah, it was there. I'm just telling one small story. It was there in my hostel room for probably for entire semester, because 4 months or 5 months is for the semester duration. For one semester, this was there in my room. Okay, these three equations. Okay, when I was studying at ISC. Anyway, but yeah, so I'm just telling you that you might take it very granted that okay, this is easy, or this is very natural thing. But yeah, if you look at any other resource, even any coaching or anything, okay, then it will be hard for you to understand. I'm trying to break it down in the smaller in the simpler words. Okay, so have you understood little bit what I'm trying to say? So basically, what this A does, you will say A is doing nothing but multiplying by sigma 1, sigma 2, sigma 3. There's a short answer. But in long, you can say yes, taking a vector from, I mean, that multiplication or not direct. It is basically first the vector has to be in the basis of V. Okay. And if it is not, obviously it will be converting in the basis of v by multiplying with the v transpose. And then this sigma 1, sigma 2, sigma 3, or after the multiplication, whatever you are getting, it is in the actually basis of u, right? But after further multiplication of u, you can convert that to the standard basis also. Okay, so that is what a matrix is doing. Understood? To any vector. So that's what this A is doing, right? Now, if you look at this diagram that we have also seen earlier, basically these are the four fundamental spaces and all, right? Now, you will be able to, even visualize it more. Now, how? You are having a vector x, right? Which you are basically breaking it v1 to vr, and I mean, in the whole this v, right? I mean, actually, this won't matter because this is the basis of the null space. Now, if you basically break this x into, let's suppose, b1 to vr, then plus vn ultimately, then these won't matter because a into this v is actually the null, right? Is actually, it will be 0. But yes, a into v1 will be sigma 1 u1, something like this, right? Sigma 1 u1. So basically this basis vector v1 is getting converted to, if you multiply with the a, it is getting converted to sigma 1 u1, like this, right? So this is a column space. So basically, earlier also we had this diagram, but now you know that if you multiply this v1 with x, okay, or if you multiply, okay, you can consider this a matrix A. So if you multiply basically any vector, if you first write down this vector in the terms of v1 to vn, and then if you multiply with the matrix, okay, then the first component, okay, will be basically first v1 will be sigma 1 u1, and then sigma 2 u2, like this, right? Okay. And then you also know that u1 to ur are actually the basis of the column space. I mean, this ax must ultimately belong to the column space, right? And you know that u1 to ur are actually the basis of the column space. So ultimately, you are getting in the column space. So anyway, if this picture is clear, okay, if this thing is clear, then you will be able to understood, and you will be able to understand, or you will be able to fit these things in the mind later on. Okay, diagram may come and go, but the mathematics should be clear to everyone. That mathematically what is happening, right? It is just taking a vector. It's very easy, taking a vector. So like this is the mathematics. This we are taking the vector, and then if you multiply the a, then if you look at the vector with respect to basis of, to start with respect to basis of v1 v2 v3, you will be getting alpha 1 alpha 2 alpha 3. But after multiplication, you are getting with respect to u1 u2 u3 basis, you are getting alpha 1 sigma 1, alpha 2 sigma 3, alpha 3 sigma 3, like this, right? Okay. Okay. So this is one popular diagram. So that's why I'm having this here. Suppose you have to start with, you have v1 and v2. Okay. I mean, yeah, you are having basically any vector. You can take any vector x, and then you will be having a into x. But x can be written as some coordinates of v1 plus something of v2. Okay. So I'm just interested in basically what is happening to v1 and v2, and then I will get to know automatically what is happening to this x, right? Because if I know what is happening to the basis vectors, then I know what is happening to all the vectors, because all the vectors can be written as linear combination of the basis vectors, and then I know that what is happening to all the vectors. Okay, so let's just see what is happening to this v1 and v2. If you multiply with the v transpose, then as you know that v transpose and v inverse are same here actually. So as you know that this this multiplication is basically converting these vectors to the basis of v. So what is the with respect to the basis of v, what is this coordinate? 1 0, right? I mean, these will be standard basis. So basically, it will be converted into the standard basis one. I mean, the first standard basis coordinate, second standard basis coordinate. I mean, basically, what I'm saying, if you multiply v1 v2 with v transpose, you will be getting e1 or 1 0 and 0, right? You will be getting this. As I told you that this is the orthogonal matrix. So it is not going to change the length, or it is not going to change the angle. So basically earlier also perpendicular, now also perpendicular, right? And earlier these were the orthonormal vectors. So length was 1. Here also delta is 1. Okay. I mean, it cannot basically change anything other than the rotation. It will just rotate. It cannot change the length. It cannot change the angle. So earlier, length of V1, V2 is 1. Angle between V1, V2, since these were the, orthonormal vectors, so that is why angle is, can you tell me what was the angle earlier? 90 degree, right? Angle also between V1, V2, 90 degree. Now, length of E1, E2, 1. Angle between E1, E2, 90 degree, right? And even you can easily try it out. So basically, if you multiply this V1 with V1 transpose, would be like this. Can you tell me what will happen if you just multiply the V1? Can you tell me? V1 into V1 transpose will be 1. V2 these two will be actually 0 because these are the orthonormal. Is this fine to everyone? It will be automatically 1, 0. Okay. Mathematically also you can see, geometrically also you can see that if you have geometrically or in other words like change of basis. Okay. With respect to change of basis also you can see that this is actually change of basis matrix, and if you multiply V1 with this B inverse or V transpose, then you will be getting the coordinates, okay, with respect to B, which are actually 1, 0. So in both ways you can see. Is this fine? Okay. Now, basically, I'm saying here, a second. So basically, you have multiplied by the V transpose, right? Okay. So currently you have multiplied by the V transpose. Now let's just so we are basically just rotating the frame. Okay, here we have rotated the frame. So ultimately we have to multiply how many things? We have to multiply U, sigma, and V transpose. Three things. But we will be starting with V transpose. V transpose first, and then sigma, and then U. Okay. And now let's just suppose sigma is there. Now sigma will do what? Whatever is there, it will stretch. Okay, let's suppose sigma 1 is larger, sigma 2 is smaller. It will stretch. This is the real. Okay, this is the real thing which is happening. Okay. So sigma will just do sigma 1, sigma 2. I mean, it will just stress some of the vectors. It will stretch some of the vector. It will basically shrink some of the vector based on the values of sigma 1, sigma 2. For example, if this is 1, 0, if you multiply this 1, 0 with sigma 1, sigma 2, this diagonal matrix, you will be only getting sigma 1, okay, and then 0. You will getting this vector, which is this, right? If you multiply by the 0, 1, you will be getting sigma to 0. So you will be getting this. So I'm just seeing what is happening to these two vectors also only. Yes, ultimately we can just take any x and then we can see a into x, what is happening with this x. But let's first understand what is happening this b1 with this b1, what is happening with this b2. So what happened? It first, got converted to the standard basis, and sorry, in the basis of v, or you can say in other words, it got rotated, and then it got stretched by the amount of sigma 1 and by the amount of sigma 2, right? And then and then you will do what? You will do the same thing, just like the any other orthogonal matrix does. What it does, it will rotate. Okay, it will only can only rotate because orthogonal matrix. So you will again rotate, and finally these are the these are the coordinates sigma 1 u1, sigma 2 u2. But if you take these coordinates with respect to a standard basis, then this will be something else. Okay. So basically, geometrically, you can understand like this. That's what it is happening. But yeah, most important part is this. Okay. You should be understanding this picture, this one. Okay. That if you multiply by the a, you are getting like this. And then what does this mean? That earlier you started with basis of b1, b2, b3. Now you are getting alpha 1, sigma 1, alpha 2, sigma 2, alpha 3, sigma 3 with basis of u1, u2, u3, right? With the basis of u. Okay. Great. So basically, if you have a, then what? If you have x, then this a is doing in the three parts. Okay, first it is basically converting on the basis of v, and then basically doing the real thing, and then converting again in the basis of a standard basis, basically. Okay, by multiplying with the u. Okay, hope that is understood. Let me know if there is any doubt in this. Okay, what this a is doing. Now let me tell you little bit more. Okay, let me tell you little bit more. Suppose there is some sigma 1 sigma 2. Okay, let me just ask you, what happens if you multiply any vector, let's suppose w1 w2, with this sigma 1 sigma 2? You will be getting sigma 1 u w w1 sigma 2 w2, right? Okay, assume, I mean, it could be any length. Okay, it doesn't matter, but assume this length of w, okay, to start with, it is, let's suppose, 1. Okay, now what is the length of this sigma into w? It will be it will be sigma 1 w1 square plus sigma 2 w2 square root, isn't it? Is this fine to everyone? Okay, so suppose these are in the increasing order, which means let's suppose sigma 1 is greater than or equal to sigma 2. Okay, or in other words, suppose if this is sigma 1 itself. Okay, I mean, let's suppose both the singular values are same. If this is sigma 1 itself, then in this case it will be sigma 1. Can you take the sigma 1 outside? If both are the sigma 1, you can take sigma 1 outside, right? Into w1 square plus w2 square. I mean, what I mean to say, it is sigma 1 into length of w. Basically, both are the sigma 1, it will be sigma 1 into length of w2. If both are the sigma 2, then it will be sigma 2 into length of w2, right? But one is sigma 1, one is sigma 2, then see, if both are the sigma 1s, then it will be sigma 1 into length of w1. If both are the sigma 2, then it will be sigma 2 into length of w2. So can you not say it is basically between sigma 1 into length of w1 to basically lesser than that? Or let me write like this. Are you getting little bit? See, what I'm trying to say, it's not that hard. I'm just saying, suppose you have 3 and 2. Okay, you multiply w1 w2. Okay, then you will be getting 3w1 2w2, right? So this vector, if I just ask you length of this vector, okay, whatever, however you donate it, actually this is sigma into w, you can donate it anything. Okay, so suppose if I ask you length of this vector, then what will you say? It will be basically, it will be lesser than equal to 3 into length of this vector, I mean length of w1, and 2 into length of w2. Basically you can say that if both are 3, then it is actually exactly equal to, if both are 3, then it is exactly equal to 3 into w1. Okay, so for example, if both are 3, if both are 3, then it is exactly equal to this, right? This is not w1, this is w. Sorry, these are w's. If both are 3, then is this fine to everyone? Okay, if both are 2's, then it will be 2 into 2. If one is 3, which means, and one is 2, it will be between 2 and 3, right? It will be between 2 and 3. So if this is sigma 1 and this is sigma 2, you can say the maximum value that it can take is basically sigma 1 into something, and minimum value it can take is sigma 2 into something. I mean, it will be between this, right? Okay. So because see, each of these coordinates are getting stretched or getting shrink by the sigma 1, sigma 2 only, right? Okay. So now let's just see this question. This is the just a true false question. Let's just see what they're trying to say here. Okay. So they're saying if A is 2 cross 2 matrix with the singular values 3 and 5, okay, there is some W in R2 with a length of W is, let's suppose, 1, then can the length of AW be 2? See, the length of AW will be maximum length will be 5 into W and minimum length will be 3 into W. Okay. It will be determined by the 3 and 5. Actually, the length doesn't change. See, I'm not considering this U and V because length and these things doesn't change with the U and V. I'm only considering with the sigma because sigma is the real thing which is changing the length and all, right? U and V, U and V does not change length. So what is the maximum length? Okay, just tell me what is the maximum length this A into W can achieve. Just a second. Yeah. Could be 3 into, sorry, 5 into W. It is only when both are actually 5. Okay. Minimum length 3 into W. It is when both are actually 3. Can it be 2? Can it be 2 of AW? So AW cannot have length lesser than 3. Okay. So this is actually false. Okay. What about the statement B? Let's just see what this statement B also. What about this statement B? Can AW be 4? Can AW be 4? The answer is 2. Length of AW will be actually lesser than equal to 5 and greater than equal to 3. Now let me ask a question. Instead of this, let me say 2. Okay. Then see in that case, actually it is 5 into length of W. Okay. Don't worry about it. It is 5 into length of W and 3 into length of W. Okay. So whatever is the length of W, you can just plug in. Doesn't matter. Length of AW should be like this. So length of W itself is 2, which is fine. Okay. So it should be 6. And then this itself is 2, right? Which is 10. So 5 into 2. And this is 3 into 2. I mean, the idea here is that it should be like this. So is this possible? What is the answer now? Is this possible to have length 4? Length of AW to be 4? Answer is no, right? This is false. False. Understood? It should be between 6 and 10. Should be between 6 and 10. Okay. So what any matrix is doing, A is doing, see, U and V doesn't change length. Okay. The only thing which is going to change the length is what? Sigma, right? Which is the real thing. U and V will just rotate the things. Okay. It is just a way of seeing the things. It is just a way of, seeing with respect to some different bases. That's all. The real bull is sigma. So what sigma is doing? It is changing the coordinates. Okay. So if I just talk about the length, then you can say the length of the resultant vector will be determined by the actually not just length, even the coordinates. Okay. The coordinates will be determined by the sigma 1, sigma 2. Okay. And definitely the length, right? I hope you understood now. Little bit you have understood. The length of this AW will be sigma 1. So you can say something like this, that let's suppose this A has sigma 1, sigma 2, sigma m like this, okay, or sigma r singular values, okay, where sigma 1 is greater than or equal to sigma 2 greater than or equal to sigma like this, right? The length of AW for AX, whatever you like to write, this will be basically if all are the sigma 1, then it will be sigma 1 into W1. But yeah, currently you can say it is. So basically, it is same as, by the way, length of sigma W, because length doesn't change for the U and V. Okay, it is same as length of sigma W. And now whatever the sigma is doing, you can just treat like this. Okay, it is basically sigma 1 W1, sigma 2 W2 like this, right? Sigma R W R, and now this is 0 0 0. Okay, if these are the zero singular values, okay, then you can have 0 0 0 also. Okay, so like this, this vector is this. Now whatever is the length of this, you can just see. Okay, if R non-zero singular values, then this will determine the length. Understood? So basically this is important. The length of AW and length of sigma W are the same. This is important because U and V doesn't change the length. Okay. So I just suggest you to watch this particular lecture once again. Okay, we have covered one important thing here, which is geometry of the SVD, what this SVD is doing. I'm not 100% sure if they can ask this directly in gate DA, okay, as a question. They may definitely ask, but maybe something like this true false question they may ask, or there could be another type of questions. But yeah, these type of things can definitely improve your thought process. Will definitely be making you more capable to crack any interview that you are going to give after the gate. After gate also, many of the institutions like IITs and IIC, they also conduct the interviews. So if you have this much crystal clarity, you will be definitely be able to crack the interviews. Okay, but it is actually the whole lecture can we just sum up into just one slide. And what is the slide? This is the slide. So basically nothing, like x is x, you're representing like this, then ax is like this, that's all. Okay, the whole lecture in one slide is this. Okay, or if you want both of the things in the same page, then you can say the whole lecture in one slide is this. Okay, it is not that hard, it's easy only. So that's all in the geometry of the SVD. Thank you, everyone.